Good evening and welcome to this webinar entitled VCE Methods Implementation Term 2, hosted by Texas Instruments Australia. My name is Brian Lannon and I will be your host for this webinar. Now, if you've been reading the introductory pre-webinar slides, you will have noticed that this webinar is being recorded and it will be available for you to download and view later on at your leisure. It will be added to the already very wonderful array of on-demand webinars that can be found on the professional development section of the Texas Instruments Australia website. So you can watch it again and again, and not only that, you can download the package of documents that has been generously and cleverly written and provided by this evening's presenters. Let me tell you a bit about those presenters. You will be hearing from Frank Moyer. Frank is a very clever fellow. I know this because I have attended conference sessions that he has conducted, and he's got some wonderful ideas, particularly on investigative tasks. You see this in the bio. A key area of interest for Frank is the use of rich tasks and investigative approaches to promote deeper conceptual learning of mathematics. In particular, in this evening's webinar, Frank will be sharing a modelling sack idea, which he calls traversing terrains. He'll also be talking about Newton's method and sampling and sample proportions. Yes, that's that probability stuff. Don't we love that? Our other presenter this evening, and the one that you will be hearing from first, is Hayley Daru. She teaches at Waverley Secondary College, and she's also very clever, and I've also attended her sessions at conferences and been amazed by some of the wonderful things that she's doing in her classroom. Read this. She's using TI Navigator, Google Forms, the Explain Everything app. That sounds like a classroom that would be good to be in. She is a regular presenter with our TI webinars and also with the conferences. She will be telling you about inserting sliders into calculator pages for the teaching of transformations of functions. She will show you about useful commands in a notes page and how to utilize that. She will tell you about inverse functions or inverse relations and circular functions. So that sounds like an action-packed evening. I think we better get into it. Before we do, though, can I just remind you and very much encourage you, you're attending the webinar live, so make use of that and ask questions. You can use either the Q&A facility, or you can use the chat window. Can I encourage you, please, to write your questions to all panelists? That way, any of us can pick it up and respond. We will be monitoring this throughout the webinar. So, Hayley, without further ado, we will hand over to you.
Thanks, Brian. Okay, good evening, everyone. Thank you for joining us tonight. I hope you get something out of this. My little section of the webinar this evening will be a couple of hints and tricks, and basically just sharing things that I've used this year in my methods classes. So I have 2 Year 11 methods classes this year and 2 Year 12 methods classes this year. So lots of methods going on in my classrooms, and hopefully you get something out of this session that you can go back to school with and use in your methods classes. So the first thing I thought I'd share with you today is inserting sliders into a graph page and using sliders to help students understand transformations of functions, which they do in both units, well, Unit 1, 2, 3, and 4, really. So let's just start by inserting a new graph page here, and Control-I is the shortcut that we can use to do that, and we might insert a graphs page here. So we might start with something nice and basic like a square root function, and I've just noticed that my letters are coming up as bold, so let me just insert a new document here and we'll try again. There we go. Okay, so you're in a new graphs page, and we might type in something like a times the square root of x minus h plus k. Now, if you've got the new software and the new version of the software is 4.2, then when you press enter here, the new software actually asks you if you'd like to create a slider. In the previous software, you had to type that equation in first and then go and insert a slider. So I encourage everybody to update their software, which you can do in a number of ways, and you can certainly be asking people how to do that. If you're not quite sure, ask in the Q&A box now and someone will get back to you. But if you have the new software, then you'll be prompted to insert a slider for A and H and K. And what we can do is change the values of A and H and K. And this is a great way to show the students dilation on the x-axis and, of course, horizontal and vertical translation. Now, when you insert a slider, it just sort of defaults to a step size of 1. So we're going up in whole numbers here, and we also have numbers from -5 to 5. But you can get the students to go into the settings here. So on a computer screen, what I did just there was a right click, but obviously the students' handhelds are a lot more clunky than using a nice computer screen like this. So if your students are using handhelds, then the way to right click is control menu. So if they hover over this and press control and menu at the same time, then that's the equivalent of a right click, control menu. If we go into settings, then we can actually choose what we want our value to start at. So I might want my A value to start at 1, and I'm interested in all A values from perhaps -10 to 10, and I want my values to increase by 0.5. You also have an option of making your slider horizontal or vertical. That's just literally whether your your slider is horizontal like it is here or vertically. Now what we can do is change, and that's a nice, much smoother view of our dilation changing. And it's a really nice way to show the students that if your dilation factor, if your coefficient is negative, then that causes a reflection. So that's just a really nice way to demonstrate that. Now, I have obviously just done a fairly basic example here with a square root function. But as you know, in Unit 1 in particular, the students are learning about all sorts of functions. So they're learning about hyperbolas and all sorts of polynomials. And you can make use of this with your Year 11s with all those different functions. I actually used it recently with my Year 12. With my Year 12s, they were, just insert a new document there. My Year 12s were learning about power functions. So I actually did this with x to the power of p on q. And if you press enter, again, you're prompted to insert your sliders there. And we spent a good double lesson looking at what happens with different values of p and q. So when p is even and q is odd. And of course, you can set your q value and then look at how your function changes when you change your p value, which was a really, really nice way of introducing this concept to Year 12 students. And they got a lot out of it, I think, rather than just, teaching them to memorize what the graph looks like when p's less than q and vice versa. They actually got to experiment with this, and they picked up things in the shape, like the fact that often, that looks like the inverse of another graph that they're familiar with. So that was a really good way to use the TI as a teaching tool in the classroom. So I hope that wasn't too fast, but that was my first point, is inserting sliders into a graphs page to help students to understand transformations of graphs. And then you just saw that you could even use the sliders to help students understand the nature of graphs depending on the power. Okay, the next little bit that I have for you today is in regards to polynomials and using commonly used functions on the CAS for polynomials. So we might insert a calculator page here and look at a polynomial. Let's do x to the power of 3 minus 4 times x squared minus 31x plus 70. Now, recently I watched a webinar that was hosted by Ham and Boizana, it was for IB, and they taught me that on the new software, again on 4.2, there's a nice little addition here that if we type in some sort of rule like this, it doesn't need to be a cubic, but if you press Control and Menu, this little maths actions box comes up. So that was Control and Menu that I pressed, and that's, as I said before, the equivalent of a right click. And these options come up for the students. So there's an option to try and factor that expression, and that will put the factor brackets around. You could have also chosen, I'll just copy that down again, paste it down here. So if we press Control Menu again, rather than trying to factor, we can try and find the roots or try and find the zeros. So all of these commands are available. Obviously, they can type in zeros. I'll get that out of the catalogue. But this is a nice way for them just to access those commands without doing much thinking about where they are in the menu. The other nice little thing is if they actually were to type in y equals and then that expression, and they do Control Menu, an option comes up now to have a look at the graph. So if we type that in, the graph appears and it automatically splits the page, which my kids really liked when I showed them that addition to the software. Obviously, a nice thing about this is that it doesn't need to be a function. So if we, were to insert a circle, for example, a circle equation, x squared plus y squared equals 5, and then we do Control Menu, it will actually plot the graph of the relation, which was a really, really nice little addition there. I am getting a little bit sidetracked. If they want to undo that after they've done it, they just press Control Z, and that should undo that. Let's come back to this polynomial. Might just shove that over there for a second. Oops, sorry. If we come to this polynomial here and use our define function, which we know we can do, might call it p of x, and define that as our polynomial, then we can, of course, use all of those commands that we saw before. The zeros command is a nice one, and they don't need to retype in the function. Zeros will find our roots, which is similar, of course, to using the solve function. Now, I'm typing these in because I can, and I'm on a computer, but obviously for the students to find those commands, as I said before, they can look through their menu and their algebra catalogue, or now they can simply just type it, press Control Menu, and those options come up. Now, the nice thing about this is that we can teach our students to make some notes pages. So I've done one here. If you haven't used the notes pages before, you can insert a notes page. Again, Control I is the shortcut, and we can insert a notes page here. They can type into this, so this page is about polynomials. Again, much easier to do on a computer, but they can do it on their computer and then transfer the file across onto their handheld if they want to. My students are very good at shorthand, so this would have said PG, Poly probably. And what they can do is actually set up a notes page here where they've defined the function, and then they've factorized it, and if we put equals there, that will factorize it, and if we press equals here, it will solve it, and if we use our zeros command, here we get our roots, which is just the same as what we were doing before on the calculator page. But now if I were to come up into my function up here and change some of these values, maybe I'll have minus 11x squared, and let's do plus 10x there, and I press enter, then automatically that filters down and changes my factored form, my solutions, and obviously the roots of the equation. And it doesn't need, as I said, it doesn't need to be a polynomial function, so they could come in here and they could type in well, it's not going to factorize nicely unless it's a polynomial function, is it? So let's do something that will. For example, it could be a quadratic, and as they learn about higher order polynomial functions, they can type in quadratic equations, etc. into here. So that's a nice little page for them to use. I think I tell my students, look, they probably wouldn't use this in an exam, but if they got really stuck and they couldn't remember, what to do on their calculator or what functions they could use, they can always open up this, and of course they can have this saved on their handheld. We don't clear out their calculators. They can have what they want saved in there. So I've actually been using with my Year 11 notes pages for revision. I think helping the students to construct a notes page is a really good way to remind them of the skills they need to know. So we did this on the other day, in one of my Year 11 classes. I gave them the job of constructing a notes page that would find the equation of a straight line if it passed through the points A, B, and C, D. And obviously they had to do this in groups, and they were testing out their notes page, and we got all sorts of error messages coming up, and they'd forgotten the command, but it was a really, really worthwhile exercise because in the end they all got there. So this is an example of one that a student of mine has put together, and if we say that our straight line passes through the points 4, let's say 4, 7, and we'll say 0, 11, for example, what happens is that it actually calculates the gradient for us, and it will also calculate the equation of the straight line. And if they go in here and change one of these values, it will change our gradient, and it will change the equation of the straight line. And they had a lot of fun putting this together and, walking around the room and seeing what the other groups had done, and overall fairly basic skill, finding the equation of a straight line for our Year 11 methods kids, but it worked out to be a really worthwhile exercise, and they went off and made all sorts of other notes pages after that lesson. Okay, the next thing I might show you, and I am zooming, but if anyone's seen me present, I tend to zoom, so sorry. If I'm going too fast, Brian, yell out at me. And if you have questions, maybe I can answer those if you want to type them into the question box. I can answer those in the second half of the webinar. Thanks, Brian. Let's have a look at inverses on 4.2. Again, there are a couple of changes on 4.2, so if you haven't updated, I really do encourage you to update your software and obviously update the kids' software. I started trying to teach something to a class and half of their software was updated and half of their software wasn't, so that quickly ended that little exercise. I had to stop and update everyone's software. With inverse relations, it's a little bit different on our new software. So let's insert a new document. If we look at something quite basic like a parabola, we can now insert the inverse relation by pressing menu and graph entry edit. And on 4.2, there's now this second option here, which is relation. So we're going to insert the relation. Now, just get out of that for a second. Our function here is f1 of x. So when we insert our relation, and that was graph entry edit and relation, we want to insert the relation x equals f1 of y. So this is a nice way to show the kids, swap x and y, and press enter. And you can see here that the inverse relation appears on, I'm just going to change the color, sorry. The kids get pretty excited when they can see that you can change the color. There we go. So what we've got now is the inverse relation appearing, and we can do a few things here. We can stretch out our original and see the inverse changing. It's a really nice way to show the symmetry in the line y equals x. We can obviously add in a line y equals x, and that will appear through the middle as well. Let me just change my color, like different colors. There we go, and this is a really nice way to show the kids that the graphs always intersect on that line. And obviously we can go back to our original function. We just need to go back into function mode, and we can change the original function. Let's make it x minus 2 squared minus 1. And again, if we have our inverse relation defined, then automatically our inverse comes up. And the kids can play around once they start talking about inverse functions and where we'd need to restrict the domain. They can put in a domain restriction at the end of their function here. So we might take the let's take the right-hand side of our parabola, and we can see that then our inverse is a function, and of course still if they intersect, they will intersect on that line y equals x. So that was a really nice way to introduce inverse functions to my year 11s, and also revising inverse functions with year 12. We had to play around with this as well. So that was, as I said, I think that was a worthwhile little exercise and a great teaching tool as well. Okay, we're going to skip now to, I just need to go and find my document. I've got some circular function stuff that I have been doing. Obviously our Unit 3 kids should have done circular functions recently, and we see that quite often we'll get questions like these two here, where we're finding the number of solutions to this equation or the sum of the solutions to the equation. And I was finding that, well, firstly, my students, when they were actually trying to solve that on the CAS, often they were just typing in solve, and then I think it was tan 3x equals root 3, and they were getting general solutions. Mine's come out with N7 because I've obviously solved 7 circular functions somewhere here in this document. Sorry about that. That was a really nice discussion with the kids, you know, what does the N7 mean, and don't write that on your paper, etc. It was nice to show the kids that they could restrict the domain, so they could say, okay, I'm actually just interested in values from minus pi to 2 pi. Now, I did that typing in pi for pi in a PD once and got this, I think I'm doing something wrong if that's the most exciting thing of my PD, but that's all right. So we can see there that that's the list of the solutions. Now, what I wanted just to show you was that using the zeros command for this type of question is good for a number of reasons. If we wanted to know the sum of the solutions or even how many solutions there are, and we've used solve, then it's quite, particularly on a handheld, quite clunky to go across like this and try and count all of your solutions. You can use Control 7 and Control 1 to get to the top and the bottom of the list. That's a nice little shortcut, Control 7 and Control 1. But it's still not great for making sure, you know, our kids in particular tend to want to make sure that they've counted all of their solutions there. So an alternative to solve is to use the zeros command. You can find this in the catalogue. You can also type it in. The kids tend to work out where it is pretty quickly when they see what it does. And if we are using the zeros command, our equation needs to be equal to 0. So they just need to transpose the equation. And then we're going to put in our domain restriction again, so minus pi to 2 pi, I think it was. And the nice benefit of this is that our solutions come out in a nice set like that, so it's much easier to see. And in addition to that, the students can count. Again, I just typed that in, but they can find count in the catalogue. And they can count, go up and case them, and it will count how many solutions they have. They can also do the sum, and it will add the solutions together. So there are a few in my class when I showed them that little command, they tended to like that. So that's just a little hint for our multiple choice questions using the zeros command. And the key here is just to remind the kids, if they're using this, they don't need an equal sign. They just transpose their equation to make it equal to 0. Okay, I think I've got about 1 minute before I need to hand over to Frank. So I'll just finish off with another circular functions thing that I did in my class down here somewhere. And this was looking at, it actually came up when we were doing horizontal translations of sine and cosine graphs. but it sparked a discussion about symmetry properties. So I inserted a graph here, and you can see I've inserted sin x is my blue line, and I've inserted the graph, or plotted the graph of cos x minus h. Obviously h is my horizontal translation, and I've inserted a slider here. Now the reason that looks a little bit different to my other slider is just in settings there's an option to maximize it or minimize it. So I chose to minimize my slider there. Now what we can do is increase h, and I had gone in already into my settings and made my step size pi on 12. So my step size is set to pi on 12. I'm interested in values from minus 2 pi to 2 pi. And if I now start changing this, the students can see this beautiful relationship between sin x and cos of x minus h. And they were coming up themselves with these, sort of symmetry properties. So they were saying things like, oh, miss, cos of x minus pi on 2. Obviously, they need to recognise pi on 2 is there. They tended to recognise that number, which was nice. And they were saying things like cos of x minus pi on 2 is equal to sin x. And again, there was a lot of, oh, makes sense now, why that symmetry property exists. Another nice one was getting a negative, there we go. So that looks like an inverted cosine graph, and they were coming up with statements or realizations that cos of x minus pi is equivalent to minus cos of x, which was, again, really nice. I don't know that it's going to necessarily help them in their exam, but it certainly, I think, did help with their overall understanding of symmetry properties. Okay, I'll take a breath now. I might hand over to you, Frank. I'm right on time.
Okay.
Looking good. And keep that chat coming. I've been busily working on the chat windows here, which is good. With Hayley, there's been a lot of interest in your dynamic notes pages, and and to generally answer with the people asking, can we use these in exams? And
as we absolutely can, and yeah, I hope. Well, obviously, you've been telling them yet, but definitely, I
seems too good to be true, doesn't
my
it?
students to, it's that moment of sort of anger and frustration when you find out about them, and why haven't I known about this? But then once you start using them, the kids really get a lot out of them. I don't know how much they do use them in the exam, but the fact that they're there and they can refer to them is something that really helps with their confidence.
Yes, it's that confidence thing, and I think actually in the exam you would hope that they could do it fast enough that they wouldn't need to refer to it, but it's something to fall back upon.
That's
Frank,
right.
what have you got for us?
Okay, thank you, Hayley, thank you, Brian, and welcome to the webinar. In my section, I'll be looking at some aspects of probability and statistics, in particular looking at sampling, and also looking ahead to Unit 2 and Unit 4. So the aim is to have a quick look at Newton's method. Newton's method, if you have a look at the third dot point in the algebra area of study, it involves numerical approximation of roots of cubic polynomial functions using Newton's method. The other thing I'll be looking at, simulation and sample proportion. So this relates to probability and statistics in Unit 1, where the study design says simulation using simple random generators such as coins, dice, spinners, pseudo-random generators using technology, and the display and interpretation of results, including informal consideration of proportions in samples. So this very much is the precursor to the statistical inference in Units 3 and 4. In Units 3 and 4, there's a whole section on statistical inference, including definition and distribution of sample proportions, simulations, and confidence intervals. And I'd anticipate that the Term 3 webinar, which I think will be mid to late July, will very much focus on this. So we're only going to be touching on the Unit 3. It's mainly related to Unit 1, the work I'll be looking at today. And The other thing, thinking ahead to Unit 4, the modelling and problem-solving task is coming up. In the old study design, there were a number of different types of tasks that teachers could set. That could be an assignment, it could be a set of application questions, an item response analysis, or a short focused investigation. In the new study design, the focus is very much on investigative problem solving and modelling approaches and techniques. And what better tool could you have to support those approaches than TI-Nspire? So I'll be looking at a task which is from the Advice for Teachers section of the VCEE website, and looking at how TI-Nspire can be used to support that. But let's look at, first of all, at Newton's method. So what is Newton's method? Newton's method, also known as the Newton-Raphson method, is an algorithm for finding successive approximations to a root of an equation f of x equals 0, where if n is an approximation to the root, then the next approximation is given by this equation down here. All right, now that all looks a bit complicated. So how does it actually work? And I think that the best way to understand how it works is to actually look at a geometric approach. Okay, so we should be on page 2.2. I apologise that my internet connection is a bit slow, so sometimes you're not seeing my screen as quickly as I'd like. So it should be on page 2.2 at the moment. So I want to find the root to this function at this point here. Now I'll use this as my first guess. So I'll call that x0. Now with Newton's method, what I need to do is to find the tangent to the graph at x0. So I'll use the geometry menu, so menu, geometry, and construction, perpendicular, and I want a perpendicular line passing through this point. I'll escape that tool, extend the line, and I now want a tangent at that point of intersection. So back to my geometry menu, and points and lines, tangent, and I place a tangent at this point here. Escape the tool, I'll hide the equation, and extend the line. Okay, so this was my initial guess, x0. Where the tangent at x0 intersects the x-axis, that's my next approximation, x1. If I want to get the next approximation, x2, I need to do the same thing again, find the tangent at this point, x1. So using the geometry menu, construction again, perpendicular, okay, and a tangent at this point here. So back to points and lines, tangent, and escape, hide, extend. Okay, so this point here is now my next approximation, x2. And if I had different starting points, I would end up with the method converging faster or slower. Now, generally speaking, Newton's method, when it works, is actually very fast and you get convergence very quickly. All right, so there I tried to illustrate how the method works. This is one I prepared earlier, so it's a bit fancier in that I've got different colours and so on. And we can see that by the time we get, whoops, so long as my starting point was pretty right, I very quickly get, within 3 iterations, I get a pretty good approximation to the root. So unlike the bisection method, which is done in Unit 1, which is very robust but very slow, the Newton's method is not quite so reliable. Sometimes it doesn't work, as we'll have a look in a minute, but when it does work, it converges very quickly. All right. So that's just, this file, by the way, is available for you to download if you haven't done so already. It'll be there for you to download after the webinar. All right, so that's a summary of the method. And this is just another example. So I'm trying to find the root. My first guess is 1.5. So x1 lands over there. I repeat the process, I get the root down there, so it's getting closer, repeat the process, and within 3 iterations I'm getting very, very close. Okay, so what's the connection between that graphical solution that we were looking at and this equation that we saw earlier? Well, it's quite simple, really. It's really just looking at the equation of the tangent at xn using y minus y1 equals mx minus x1. We substitute xn and f of xn, and we get this expression here. The tangent intersects the x-axis at our next approximation, which is xn plus 1, 0. Substitute into the previous equation so that we've got 0 in place of y, xn plus 1 in place of x, rearrange, and bingo, that's where it comes from. So it's not really, even though it looks like quite an ugly recursive definition, it's actually quite simple. All right, so how could we do this using a spreadsheet? Here I've set up a notes page, same sort of thing as Haley did. I've got my starting point here. Actually, I might change that to 0.7 so that it converges a bit more quickly. And I'll set up my spreadsheet. So xn. So xn, I start with my initial value x0, which I defined in the notes page. So I should find it here in my variable list. So here, I need f of x0. Now x0 I have in cell A1, so I can just type in A1, and the f dashed of xn. Now I define, going back here, I define the derivative as g of x. So if I do g of A1, I can work those out. Now, to get my next iteration, it's my previous answer, which was in A1, minus f of xn, which was in B1, divided by f dash of xn, which was in C1. So I have my next iteration. Now I could just fill down to repeat this. Now, if you're doing this on the handheld, if you want to multiple select, hold down the shift key. So shift, left arrow, multiple select, and there's a number of ways of filling down. My favourite way is just to control click, then down arrow, bingo. Now, because I used relative cell references, I used A1. When I fill down, I'll do shift, whoops, try again. Shift, select those, control click, fill down, and my formulas will update, and we see that we very quickly converged to a root of 2, and we can see that f of xn was 0 where we would expect it to be. Okay, this is the same spreadsheet example, except that I've used a slider to change the starting value. So as you change the value, the starting value of the slider, the spreadsheet will change. And this example here shows the spreadsheet and the geographical solution side by side, so students can see the two together. And the following examples show that sometimes convergence doesn't happen. So for example, if at any stage you hit a turning point, whoops, escape out of there, if you hit a turning point, then obviously the process stops. Or you could have non-convergence simply because you chose the wrong starting point. So in this example, you can see that you get into an infinite loop. So the method doesn't always work, but when it works, it's very fast and very robust. Okay, now the next thing I wanted to have a look at was this example from the Advice for Teachers section of the VCEE website, and it's a very old problem. It used to be called Bushwalking with Kim, and in the new study design, or in the Advice for Teachers for the new study design, it's now called Traversing Terrains. So the problem is that the bushwalker wants to go from A to B, and it can travel, the bushwalker can travel faster in the clearing than in the bushland. So what is the optimum path? So the question is something like this: a bushwalker travelling from A to B, which is a straight distance of 14 kilometres, is using the path APQB. She can travel at an average speed VB in bushland, VC in the bush, VB in bushland, VC in the clearing, and speeds of up to 5 kilometres per hour in the clearing. And the question asks, using reasonable values of VB and VC, find and describe routes which for which travel time is a minimum and compare to the direct route. And interestingly, the question is not one that has a single correct answer. There are many possible answers, and so it's a very good question for investigation. And I guess it's the sort of question that perhaps we should be asking in the new study design for the school assessed coursework. Okay, now using TI-Nspire, we can solve this whole problem. We can investigate this problem using geometry. So here I can change the path by changing the position from A to P that the bushwalker will walk. Right? This is the same thing, except here what I've done is I've also calculated the time. Now the way that, so as you move the position of V, you can see the different, the total distance travelled and also the time. So if you take the direct route, it's not the route with the minimum time. Now, how did I get the geometry page to work out the time? I simply used the calculate. So there is a function called calculate, which I haven't got time to go into today, showing you how it works, but you can use that to calculate the time dynamically. Now, for this problem, I've also defined a variable x, so the distance from R to C, which is the same as the distance from R to P, I've called that x because when I do the the algebraic solution, I'll do so in terms of x. So x is just this distance from R to P or R to C. All right. Now, the other thing I can do is I can animate that point. To animate the point, you just go to the point, Control Menu, Attributes, and you choose the unidirectional animation speed. You set an animation speed 1 to 9, 1 being slow speed, 9 being the fastest, and bingo, you can animate the point. And when you animate the point, you get this little control button as well. And what I've done is, as I change the value of P by animating the point, I'm actually going to capture the value of X and the time and the distance into this spreadsheet. So as the point moves, it will populate that spreadsheet. And as it populates that spreadsheet, it will plot the points on this scatter plot. All right, so let's go back to here. I animate my point, and as the point animates, it populates the spreadsheet, and as the spreadsheet becomes populated, then you get this scatter plot here. I'll stop that. Okay, and using trace, students can either have a look at their spreadsheet and see where the time was least, or they can have a look at the graph. So in the graph, if we go to trace, graph trace, they can find the minimum time. So the minimum time seems to be when X is roughly 2.1, it's about 6.38 hours. Okay, so that whole problem was solved without using any algebra whatever. It was all done using dynamic geometry. And I think that that's the sort of approach. I guess when we are setting problem solving or modelling tasks, I don't think we should be specifying a solution method. I think we should give the students the tools, i.e. TI-Nspire, and let them investigate a possible solution method. It might be algebraic, it may not be, maybe a combination. Okay. The other thing I did...
There's more than one way to skin a cat, Frank.
Absolutely, absolutely. And the other thing is, of course, I've got sliders here so that you can change the speed that the bushwalker can walk in the bush and in the clearing. And you can see that even with given a particular path, just by changing the speed, you can see the difference in the time. Okay.
The connectivity is terrific, isn't it?
No, absolutely. I think that's the power of TI-Nspire. I think we could do this using, say, Geometry Sketchpad, but then it's just geometry. With TI-Nspire, you can link this with your algebra as well, which I think is where it's really powerful. So,
and the spreadsheet that you've also tied in, yeah.
And the spreadsheet, exactly. Whereas I can tie that in, what I've been doing with the geometry and the spreadsheet, with an algebraic and calculus approach, where it's in terms of X. So I've defined the distances, formula for the time, and I can, as I change using the sliders, this is a notes page similar to what Haley was using. and you can have sliders directly in the notes page, and you can see the minimum time and the value of x for which time is a minimum as you change those. So you can link the algebraic, the spreadsheet, and the geometric approach. Okay, and the last example I want to have a look at was sampling and sample proportions. So let's assume that in a particular in a large population, 30% of people are under the age of 25. I want to take samples from this population and investigate the distribution of sample proportions, because every time I take a sample, one time I might get 25% in sample 1, might be 35 in sample 2, and so on. So it leads to the idea that the sample proportion is a random variable that changes from sample to sample. So you've got this you've got this file here, and there's also a Word document that accompanies this that goes into the theory. But what I want to have a look at is this little animation that I've come up with. So if you want to do a simulation for sample proportion, then it's really just using random binomial. And the reason it's binomial is that either a person chosen from the population is under the age of 25 or they're not. So every time I hit the enter, I see that the proportion jumps around all over the place. Okay, and I've done this time. I've done the same thing, except I'm going to capture those values in a spreadsheet. So as they get captured in the spreadsheet, I should see the distribution of sample proportions appearing. Okay, and this is one I prepared earlier, so I've already done a couple of hundred, and we can see that it's fairly symmetrical. So if I can fit a bell-shaped curve over that, and we see that it fits sort of fairly neatly. And if I change the dot plot to a normal distribution curve plot, which gives the expected value of z against the actual proportion, the closer it is to the line, the better it is to a normal approximation. And the last one just shows the effect of changing the sample size. So as I change the sample size, I see that the spread of the distribution of sample proportions becomes less. So that file is there for you to have a look at. I've only gone through that, just giving you a taste of what to expect in the Term 3 webinar, because in the Term 3 webinar, I anticipate spending a considerable amount of time just on sample proportions. And I think my time's well and truly up, so thank you very much, and it's over to Brian.
Yeah, thanks, Frank. And once again, terrific activities. Yeah, certainly a feature from the sessions of yours that I attend, Frank, is the investigative activities that you come up with. People, there's been a lot of interest, or actually for Frank and Hayley, been a lot of interest in what you've been saying and questions through the Q&A and chat windows. I've been busy on that. I do apologise if I haven't got to answer your question, because it has been busy there. Let's just do a couple of reminders to finish up. And can I remind people that as they exit the webinar, they will be taken to a page where they're asked to give some feedback. We do value your feedback, because we use this to to influence the design of the ongoing webinar program. And also, please, if you're wanting more of these activities, I know both Frank and Hayley and myself have posted activities to the Australian Curriculum Inspired and the Senior Curriculum Inspired components of the Texas Instruments Australia website. You can find that website, I expect you already have, find that website just by Googling Texas Instruments Australia. Some people have asked about downloading the latest operating system. That's operating system 4.2. That is also on the website. Look for the section that says products, go to TI-Nspire and download the operating system for your device from there. Bear in mind, we have our upcoming webinar program. I think, Frank, you've got one in 2 weeks' time, is that correct?
That's correct, Specialist Maths.
Specialist Maths. So those of you teaching the Specialist Maths, I will encourage you to enrol in that. And remember also, I was going to take you to the website there. Remember also, please, that you will be getting your certificates following delivered to an email box near you shortly following this webinar. So good evening all. Please visit the website to see what's coming up. Bear in mind especially the upcoming webinars and the Australian Curriculum and Senior Curriculum Inspired activities. Good evening to all, and thank you to our presenters.
Thank you.